Yeah, thank you so much for such a great intro. Thank you for coming today. And we are really excited to take you on a journey of retail, NLP, transformers, and how we cook this all together. So let me start from introduction. So this talk is the result of work and collaboration of two companies. And I think it's worth to spend some time describing this. So the first company is one of our portfolio company we invest. It's called Spins, and they exist for a market for more than 20 years, and they're like one of the biggest provider of different services for retail in US. And another company is us, Georgian. So as it was mentioned before, Georgian is a VC firm. So first of all, we invest into companies during the growing stage from B2C round, but also what is unique and what is the key differentiator of Georgian is that we have our own internal R&D team, where part of our team is building a software product for our portfolio companies. So we not only invest into B2B company, but we also B2B company itself, and we also operate our own production, our own product, our own services. And another part of R&D team where we use Rohit working together is actually applied research team, or we right now call it like AI lab, where we work with our portfolio companies on a different ML problem and ML challenges. And it's usually a spectrum from like very, very basic companies where we help set up the ML team, hire the first ML scientist, find the problem, to like completely different side of the spectrum where we work with the very advanced companies where they already have a huge production, 1,000 models operating every day. So this is what Georgian is. So basically VC firm plus R&D team where we help our companies to increase their valuation. So this is a little bit introduction and a little background. I think the problem we're going to describe today, I would give like a very, very brief business context about this and then pass it to Rohit to talk about the actual ML statement. So imagine the next setup where Spins operate. So you receiving the data from more than 600 different retail chains in the US, and what are you selling and how you deliver value from this data? You're building in one standardized database of retail items on top of which you build inside and which you also sell itself. So because most of the people work in the data space here, you can imagine when you get data from different chains, different store, different location, you have a lot of challenges, right? So for example, formats are not there. Like some retail chains fill some data, some doesn't fill. Of course, data is also incomplete. They might come in like in a different time frame. So we always have a delay. Data not arrive at the same point of time, and so on. So imagine that it's kind of a zoo of different data formats, different source, and the volume data is quite huge. So the business problem is actually take this huge variety of different data formats from different locations and transform it in a one actionable database, which you can then sell as a service and on top of which you can build insights. So, and the data in this database should be very simple, it should be complete, it should be clean, it should be standardized, and it should be reliable because you are going to, like, clients of Spins are going to base their business decision and their spendings based on this data. So this is very, very brief formulation of what the problem is. Imagine we have a huge amount of data coming in and we need to build a one single standard data set from it. And how it's done before. So before it's done manually. So Spins have a lot of manual workers who actually go over this data, spend enormous amount of time, enormous amount of cost to actually build this data set. So they can resell it, but clear next steps here for this kind of business is to try ML. So this is a common effort of PI, product intelligence team from Spins and our Georgian data science team. So on this, I will pass it to Rohit on a ML problem definition.
Well, thank you, Kyryl. So Kyryl gave us a good overview of the kind of industry Spins operates in and the kind of data sets and the challenges that Spins deals with. Now, what product intelligence means is once you have a database with all of this data, what we want to do is we want to extract certain attributes about these descriptions. These attributes can then be taken back to Spins' customers, and then Spins can sell it to these customers for better product-driven insights that can drive businesses. So what defines a product at Spins? Take this Natural Valley oatmeal picture as an example. What Spins really cares about is, given this kind of a product, we would like to extract these product attributes. Now, mind you, when the data is coming in from retailers, these attributes are not present in the data set. It is Spins' responsibility to extract these attributes, given the data that's coming in huge volumes. Brand, as you can see, Nature Valley, it's very apparent from the image. The pack count of 6, again, information that's embedded in the package. Similarly, unit of measure, as you can see, it says OZ, which is shorthand for ounce. And then unit size is a computed attribute, meaning there are 6 packs of 1.24 ounce oatmeal squares, so you multiply them, so the total unit size becomes 7.44. Now the task is to extract all of these attributes. However, Spins do not get any images. As mentioned before, we are getting textual descriptions, and the goal is to extract all of these attributes from the textual descriptions. In this case, you can see the description is very nice. It's clean to an extent because it says Nat Valley, shorthand for Nature Valley. SFD means soft, BKD means baked, and so on and so forth. So imagine that you get these kind of descriptions on your screen, and you now have to figure out a way to extract the attributes that you see on the right-hand side of the screen. A quick solution that comes to mind is, why don't we just look for brands? Why don't we just scan the string for finding the right brands? Because we already know that, okay, these are all the brands that we deal with. These are the brands that we have seen previously in the database. Why not just do a string search? And that is a solution. But for the sake of this talk, we will be focusing on the attribute brand because it's to me, it's the fun attribute because it has a lot of challenges. So the goal is we would like to identify the brand attribute from retail product descriptions. And here I'm showing you a few examples of what that means. So given a product description, we want to find the mapping between product description and brand. So it's a classification problem, to put it in simple terms. But you can imagine data is very noisy. You can't expect descriptions to follow a particular format. It's going to have a lot of variations that we have to deal with while creating the models. And to make the problem even more challenging, there are 86,000 brands in Spins' database. I'm pretty sure all of you are aware of the ImageNet database, where the challenge is to classify 1,000 classes. This is nothing, it's just 86 times harder of a problem. And to make things even worse, almost half of the data comes from the top 1,000 brands. And the latter half comes from the other 85,000 brands. So that already tells you of the long-tail nature of this problem. There are long-tail distribution, meaning there's going to be immense class imbalance. So how do we go about, figuring things out given this kind of a challenge? And finally, I showed you the example of Nat Valley soft-baked oatmeal squares. These are just some of the other forms or descriptions that the same example can take. And the best example, in my opinion, is the very last one, where you just see a string of digits, and now you have to extract whatever information you need. So it's a beautiful nightmare. But anyways, I know we are at a machine learning summit, but it never hurts to start off with a rule-based system, and that's exactly what we did. What we did was we looked at the data, and as mentioned before, you could literally do a lot of string matching, right? You could extract, you could look for substrings such as PK, meaning pack, OZ meaning ounces, and then simply look if there are any digits or numbers that comes before these units of measurement and simply extract that. So by making such rules, we created these efficient lookup tables. And I'm pretty sure like if you have worked with strings, you know that the tree or the nested tree, I don't know whichever way you pronounce it, is a very common data structure to very efficiently look for patterns in a string, right? It's substring matching, substring pattern matching. It gives you constant time lookup and other benefits. So we employed all of that. We took into account a fuzzy wuzzy Python package. It's kind of the golden standard these days for any sort of string matching. And then what fuzzy wuzzy does, it gives you a score between 0 and 1, implying how similarly two strings match, how closely they match. So once we get all of these scores, we literally manually handpick for which score we get the highest accuracy, and that's how we built this rule-based system. So you can imagine a lot of pain and labor went into building this first POC. To our surprise, we managed to get a 77% accuracy. Again, remember there are 86,000 classes, so getting this kind of an accuracy was mind-blowing to me at least, although I had a lot of challenges convincing my stakeholders about this, but that's the talk for a different day. But there were a lot of drawbacks in this model. First of all, multiple brands can have the same product description. What I mean by that is, imagine you get a description chocolate biscuits. That could mean Oreo chocolate cookies, or that could mean anything else, right? There are so many brands that make chocolate cookies, and you could have the same description. So how do you break the tie in those situations? That's the challenge. String matching can produce a lot of false positives. Again, going back to fuzzy wuzzy, it's amazing, but then it has its own shortcomings, and we dealt with the false positive side of things quite a bit. As I said, we had to manually pick the threshold, which you can imagine as and when new data comes in, that particular threshold is going to affect the performance of the model downstream, because we don't know what this new data looks like and if the threshold that we picked is right or wrong for the new data that's coming in. But the most important drawback is the fact that the predictions are not probabilistic. You can imagine what we're doing is string matching. If there's a match above a particular score, this is the brand, right? So in no ways is the rule-based model telling me how confident it feels about a particular prediction. And that is important for us because the goal here is to automate tasks. If we do not know whether a model is confident or not, then we cannot say, okay, let's just automate these items. We don't need any human intervention. So that's a huge, huge drawback. The second drawback, it's hard to scale and maintain. Every month when new data comes in, you cannot expect people to look at millions of samples and then handpick rules so that they achieve a 77% accuracy. So that begs the question, can ML help us solve these problems? At the end of the day, we are doing a lot of pattern matching, and deep networks are basically the holy grail of pattern matching. So can we leverage transformers? And that's where Hugging Face comes into the picture. By a show of hands, how many of you have heard of transformer networks? Very quickly. Okay, so it's almost a 50-50 split. And again, by a show of hands, how many of you have actually used a transformer network and put it in production? Oh, that's okay, maybe 5% of the room. Great. So to give you an idea of what transformer models are, in the space of natural language processing, they have basically revolutionized all kinds of tasks, be it classification, regression, generation, summarization. Transformer models have become the de facto standard of the industry. And there's also this place called Hugging Face, which is beautiful. It's like a hub where all the latest research that's happening in the world of transformers get uploaded to. So you get direct access to architectures, checkpoints, even code that shows you how to use these transformers for your own use cases. So highly recommend giving this a check. Although we are not from Hugging Face, I'm really selling Hugging Face right now. So what we did for this project is we took the BERT transformer model. BERT is from the paper, Attention is All You Need. It's a very common paper that came out of Google back in 2017. And since 2017, there have been a lot of iterations or variations on top of BERT. So what we did is we took the problem, launched a bunch of experiments using not just BERT, but different variations, different architectures of BERT, distill BERT, tiny BERT, squeeze BERT, there's so many of them. But at the end, it was the BERT variation that simply gave us the best performance. So we took that. We followed a very similar training regime where we took 80% of the training data at our disposal. And we hoped, the hypothesis was, this transformer model would be able to learn the underlying patterns as opposed to us feeding those patterns into the rule-based system and then hoping things would work. However, on evaluation, you can see that the transformer model really struggled. The performance decreased from around 77 to now 55%. And what we noticed is brands that have very low samples are almost never correctly identified. Now, this is somewhat of a dilemma, right? Like you would imagine, it's a deep learning model, just throw data and it's going to work like magic. But these networks also come with their own shortcomings, one of which is class imbalance. You can take pre-trained networks, you can fine-tune them on your data, but if your data has only 1 or 2 or 3 samples for a particular class, high chances that the network is not going to get it right. And that is exactly what we saw. What the transformer ended up doing is it ended up over-learning the classes for which we have the most data samples. As I mentioned at the very beginning, 50% of the data comes from the top 1,000 brands. And the transformer network just honed in on those 1,000 brands and just learned everything about those brands while ignoring everything else, right? So that explains the drop in accuracy. Rule-based model, on the other hand, even though it's not good, it still can handle class imbalance. Why? Because it's simply doing a string matching check, right? So even if you have just one description for a particular brand, if that description shows up during inference, it's going to find an easy match and it's going to find that one brand, right? So that kind of explains why there was this delta between a rule-based performance and the BERT transformer performance. However, there are benefits of the transformer model. Unlike my rule-based model, transformers give out a probability score between 0 and 1. It tells you how confident it feels about a particular prediction. What this means is, again, going back to the idea of automation being the holy grail, what I mean by that is accuracy is amazing, but at the end of the day, if you do not know for what percentage of items the model is confident, you cannot automate any processes. Why? Because if the model is not confident in its predictions, you would still require a human being to go and do a check. Is this correct or is this wrong? But if the transformer model is able to tell me that, hey, I'm confident that this description belongs to this brand with a 95 or even a 98% confidence, then I know that, okay, for this description, I can simply put it aside because there's no need for human intervention. The model is very confident, and I know that whenever the model is confident above a particular threshold, it gets it right all the time. So automation, again, being the key metric that we're trying to solve for. And finally, the transformer model is more scalable. So as and when new data comes into the pipeline, you could just retrain it. You could retrain it on a particular cadence every month as and when new data comes in. And Kyryl is going to touch up on that a bit later. So because, again, we had this notion of high confidence predictions allow for automation, it basically made our lives easy, and the stakeholders seemed confident in this kind of an evaluation, even though the accuracy took a hit. And for these reasons, we proceeded with productizing the transformer network as opposed to the rule-based network. Now with that, I'm going to pass it back to Kyryl to talk us through the production efforts.
Yeah. Thanks, Rohit. Okay, so once we're done with research and once we're done with developing model, let's say it's not done, but we're at the point that it's good enough to provide some value to the business, we actually might move to a last mile deployment. And this is like a really popular buzzword, MLOps right now. I think you heard anywhere. Just curious, like, if you close to research and actually train network, work with data, could you raise a hand? How many people, it's curious, like close actually like researchers? Okay. And could you raise a hand if you're more close to production, to engineering, to actually deploying model, working with them in production? Ah, interesting, yeah, interesting dynamic. So the things I like in Georgian also that when we do a project with our portfolio company, we're doing it end to end. So we make sure that research is done, we make sure that it's in production, make sure that the production is actually in a low maintenance mode, so you can support it, and there's a actually team inside of our portfolio company which can then update and support this model. So this very high level diagram of how we put this set of model into production, and Rohit described one model for a brand identification, but you saw in the picture before that there is a lot of information we can extract from the one retail item. So this scheme is actually about set of different models. And yes, for brand identification, we end up using bird, but for different part of the information extraction, we use different models. Some of them are from bird families. For some, we use distilled bird. For some, Roberta. Some of them might be like more not such sophisticated models. So this productization scheme is basically a framework where we put all our models into production, and it has three main components here. So first one is actually training, of course, right? Because we not only train model and then deliver checkpoint somewhere so somebody can serve it, we also make sure that all training code is tested. It's live on a platform where you can retrain regularly. We keep versioning and we keep lineage. So basically we have different data, different point of time, and we have different version of models, and then you might select which one you want to choose for a serving. So very, very high level, and we have a very nice article where we describe all technical details and implementation under the hood, but if I describe it high level, we work in the next way. For data storage, we use combination of GCP buckets and BigQuery, where we get constantly data ingest from other team or from retail directly. For our training code and automation of the training code, we use framework called Airflow, which I think pretty much popular and one of the most, like it's not very specific for ML, it's more general case, but I think in this case we went with Airflow because rest of the team in Spins use Airflow and they have like 1,000 docs there, so we just adopt this. And we package all our trainings with help and orchestrate all our trainings with help of Airflow on top of Kubernetes platform. So we wrap everything into the Docker and then Airflow just spin up training. The final doc, directly like a safety graph, how we actually structure retraining is, it's kind of mid-size. It's have like a 50 steps. So we have 6 models in total for extracting this information. So this doc is actually managed like a 50 steps from where 6 of them are actually model training. And then this doc also assess model, write some monitoring information, and create a new version of the model every time we get the new data. So this is how we manage training, and we retrain once a month because of the cycle when we get the data. Empirically arrives at like once a month is the best trade-off for us between the frequency of when we retrain and keep the best possible accuracy and the best possible model performance. Once we retrain all of this, we save model, we save new model version, we want to make it accessible, and for this we use pretty much standard serverless approach. We use a tool called Google Cloud Run, where it's very similar to Kubernetes, but you actually don't need to care about the underlying infrastructure. You just define, okay, this is my web server, this is my model, and this is my autoscaler. And I would like to, depends on my load, scale from 1 to n instances. I think our setup for this platform, for this case, is we scale for all 6 models up to 100 instances at the peak load, and we usually keep like 1-2 instances just to handle some like day-to-day requests. So it's like, so the latency, beginning latency, it's not such slow. And of course, Docker is the main way of delivering model here. You also can choose which version of the model you might use. By default, you're going to use latest version. But if you think that the previous model is more better, you can always revert back and actually serve the previous model, a previous version of the model. And we have custom build monitoring on top of this, where we actually explore prediction and see that it's actually right and it actually makes sense and there is no critical outage and critical down in the performance. And clients is basically simple REST client from another team, which actually send us data for prediction, then save it in their internal storage, and then on top of this, they can run their analysis and build this database. So pretty much standard, very, very high level description of how the system works, but I like that it works end to end and have like all basic components. Retraining, inference, we keep all versioning, we keep all lineage, and we monitor that everything is going well. And the nicest part about this is that the effort to maintain this is actually not such high, and effort to update this is also not such high. So we try to keep the actual experimentation code and training code very close to the version of the code we use to serve into production. So what is the impact? What we get at the end with this problem statement, with this research, and with this productization of all of these models for different part of the products. So I think the first and the most important one is the automation we're able to get. So at the beginning I mentioned that they used to use human labelers to actually extract this information. Right now we're saving 30% of the time of these people, so they actually can label even more data, or they can start doing some other useful task where machine learning actually can fail. So we were able to automate 30% of the income data from volume we receive, and this is right now processed automatically with the error which we agreed with our customers that is acceptable. I think the error we spoke with them is actually 2%. So when human label it, we said like, okay, the 2% of the actual records in this database might be incorrect. So we were able to automate 30% of input data with this error. Of course, with this automation, you can reduce time and cost because to support the system, again, it's not such a high maintenance fee, so you can run it for a while in production. The infrastructure cost is pretty much reasonable, and it's quite dramatic saving in our cost and time. I think also because part of this project is automated, you can faster build this database and deliver insight for your customer even faster, which increase trust and increase actually customer satisfaction. And I think last but not least is that as long as we know, Spins is the only one retailer who use BERT and use machine learning to automate creation of this industry standard database, which is quite unique and provide like really nice brand recognition for them. Again, we have a very, very detailed blog post where everything we discussed today is actually described in a very detailed way with technology, with numbers, with much more granularity. But as for now, we're really happy to get your questions. Thank you.
First of all, a really good presentation. Thank you, guys. So if I understand your problem correctly, it is given a set of textual descriptions, you will have to extract attributes from that. The attributes being product description, ounces, unit of measure, and all that. So I see this problem as a sequence labeling problem. Have you tried conditional random fields?
Sorry, could you?
Conditional random fields?
No, we haven't actually tried conditional random fields, but I do agree with you that it's a very sequence to sequence kind of a learning paradigm. And in fact, for one of the other attributes, which is unit size, we went down the route of exploring the encoder-decoder model. So given a product description, as opposed to classifying what the unit size should be, we learn the sequence. It's almost like going from English to French. We are going from product description to the unit size. So we do have a class of network, not for brand, but for another attribute where we went down the road of sequence to sequence.
Yeah, I had the same problem, like not on the product descriptions, but on the prescription parsers. The prescriptions that the doctors write in North American hospitals all over the world. So I had the same issue, like every doctor has its own style of writing. The same prescription, like take one tablet a day for 20 days, would be written in umpteen number of ways. So I figured out that the transformers was not working issue. So I went on the route of going for the conditional random fields coupled with the bidirectional LSTM. So that worked pretty well. Maybe you could try that as well.
Thank you for the recommendation.
Yeah. And
There was another question over here.
Thanks for presentation. It was very nice, and I have several questions. But to start with, did you happen to consider combining the rule-based algorithm and deep learning?
That's a great question. We did have the idea of ensembling the two techniques. I will say that there was some discussions surrounding how do we combine the probability scores that this model gives and the scores that we're getting from fuzzy wuzzy, because they're not the same in a sense. Like
I'm just guessing score can be converted to or considered as probability.
It could, like you could basically get like a bunch of scores and then do like a soft max to get an essence of probability, but for some reason, like we did try that. This is not to say that we didn't go down the path of ensembling, but then just combining the two, we were not, first of all, very confident in what these scores represent. So that was a difficult conversation with the stakeholder. And second of all, we did not see any significant boost that would justify the added cost of putting that into production along with the BERT and then combining the results, right? Because research is one thing, but at the end of the day, it's the user experience that also matters. And we don't want to overcomplicate things just because we can.
The first model we put into production for a brand was actually rule-based. Then we put another one and like start thinking how we can combine them. And after like long different feedback cycle, we decided to revert back only for ML.
But I would say that there are thoughts of different ways of ensembling, one of which is we know that 1,000 classes, the top 1,000 are the ones that this particular model is very confident on. So why don't we have like a cascaded transformer networks? The second one can focus on the... Exactly, the other way around. So those are talks, those are there in our plans. We just haven't gotten to implementing yet.
Okay, and also I wondering if usually the high confidence leads to the accuracy in the BERT model, and the other way around it, if you see low confidence in the BERT, it usually leads to the low accuracy. Is that it, or do you see other cases as well? So that you find 45% accuracy inaccurate cases from the BERT model, right?
Right.
So then usually those are linked to the low confidence, low probability in the BERT model. Is that it? Or the high confidence can also lead to inaccuracy?
Okay, so in our case, so that's the evaluation that we did. So if I'm understanding your question correctly, what you're asking is, like, how does accuracy trail with like high confidence prediction? So that's a great question, by the way. Like, so what we did with this model is we found that particular threshold in the probability score space that gave us a very high accuracy, and that accuracy was established by the stakeholders. As Kyryl mentioned, when humans are annotating these products, they have only a 2% error rate. That's a very high target. So what we had to do is we have to say that, okay, now that we have all the predictions, let's filter out the ones that have a probability of greater than 0.95, 0.96, whatever. And now let's see what's the accuracy of this bucket of items. Is that greater than 98%? Meaning, is the error rate lower than 2%? If it is, then that marks as, okay, this can be automated. Because now we match human performance, and so we can now bring in automation. So that's the way we thought about the trade-off between accuracy and then picking a threshold that gave us the 2% error rate.
One of the reasons I'm asking this is that if you think about how to deal with the low confidence bucket,
right.
And you might want to consider to link to rule-based model in those cases.
Right, yeah. Again, this I think brings us back to the question of how do you incorporate rule-based into the system, but would love to, chat more. No worries, yeah.
Hey, thank you. I understand the implications of ensemble, but where did you start your BERT or transformer data set from? Did you start it from the scratch, raw data? Or did you use the data that you have already labeled at 77% and then fed it into that? So which one was it? And the second part of the question would be, what did you do with the minority classes in your BERT? Did you do anything? You just abandoned them because they're not enough?
I'll answer the second question first. We did nothing.
Okay.
As of yet.
Okay.
And to answer your first question, we started off with a pre-trained model only because we are again looking at English descriptions. So the transferability of using a pre-trained BERT gave us some boosts as opposed to training these descriptions from scratch. So we did that in analysis and we didn't see the delta to be high enough between fine-tuning and pre-training.
But your label comes from your either ground truth or from the model that you have already rule-based labeled. Did you use that label or did you use your ground truth label?
We used the ground truth label.
What stopped you from using the rule-based, the label that coming at 77% accuracy from your rule-based model? Why you didn't use that label? What stopped you?
I mean, the rule-based, whatever it's predicting, so the way we compute the 77% accuracy is by comparing the rule-based prediction against the ground truth prediction. But now we have more than just the 77% of items at our disposal from ground truth. So it's the same label space, right? So we just went with the labels that we have from the data itself.
Your 77% was from your training data set,
Yes.
not from your internal.
Yeah.
Okay, that makes sense.
Yeah.
Thank you.
Okay, we've got time for probably one quick question down here. And then
Two more questions. Yeah.
Hi. My question is on training of BERT. Is the task just classification task? Oh, is the BERT training you did, was it on just classification or was there any domain adaptation on retail industry or like any fine tuning?
Yeah, so it was primarily classification, but then of course we had to do some sort of hyperparameter tuning on top. So that's where we ran a bit of a grid search, and then whichever architecture gave us the best result, that's pretty much what we settled with.
12-layer? So it's a full 12-layer BERT? Like
Cannot.
it's 12-layer BERT, then
Okay.
BERT base.
This is the BERT base uncased
It would
network.
be interesting if you can share some, in productionizing, how did you come across any runtime issues or like?
The production expert.
This is a good question. So as I mentioned, for a brand, we come up with a BERT only, but for different attributes, we also use distill BERT. And yeah, of course, to put BERT only, even like just because it's like weights around 500 megabytes, right? It's already like might create some latency issue. So yeah, because it's internal facing service, the one we care is actually throughput and not the latency. So as long as we can get like a big enough throughput, the latency is not a big issue for us. And I think also worth to mention that the input for this model is very small. So if you have seen, there's like a very, very like tiny description. So we actually send like a huge batches of around 1,000 batches into the input, and it can process like really fast under like couple of seconds, and the latency is not issue. But with the different attributes where the description is much longer, we actually use distill BERT because of the sequence length is much longer, and we need to process it faster. So answer is yes and no. Latency was the issue in other cases. In this particular cases, BERT is giving us normal enough latency.